So hopefully we don't run into any of the technical problems that we had on Monday. So I don't really have anything planned. I'm just going to do whatever questions that you guys request. So if you post in chat the questions that you want me to go over, I'll start going through those. Let's get some lemonade. Actually, save the lemonade, get some water. Okay, 2017 problem number 4 is the first one. So, 2017 problem 4. Okay. So, in this problem, it says that you have a cylindrical shell that's made out of a material with constant resistivity rho 1. The shell has an inner radius of A and outer radius of B. It's surrounded by another cylindrical shell with inner radius B and outer radius F and constant resistivity rho 2. A battery with known voltage is connected as shown, so that the constant current is made to flow radially out from the inner surface to the outer. The length of the cylindrical shell is W. Find the current. Okay, so this is a problem that is going to have to do ultimately with finding some resistance. And so I'm going to start by writing down the microscopic form of Ohm's law. So that's to say that E is equal to rho times J. And ultimately, with a lot of these problems, what we want to do is we want to get to talking about some difference in electric potential. You probably see a theme with a lot of these questions, whether it's a capacitor problem, or it's a resistor problem, or it's a Gauss's law problem with insulators and conductors. A lot of times we're interested in finding a difference in electric potential. And so in order to do that, if we write down that equation, we have delta V is equal to the negative integral of E dot dl from R1 to R2. What we realize is, in order to do that calculation for the difference in electric potential, we need to find what the electric field is. And so for this problem, because we're talking about resistivities, that's going to lead us to using the microscopic form of Ohm's law to find what these electric fields are. So just to draw what we have here, we have, this is cylindrical. So we connect some battery to the inner surface here and the outer surface here. And ultimately what we want to do is we want to find what the current is that flows from here to here. So we know that there's some resistivity rho 1 here and some resistivity rho 2 here. And so what that means is ultimately we're going to have two different electric fields, one in the inner shell and one in the outer shell. So for both of those, we're going to use this E is going to be equal to rho J. We also know that I is equal to the integral of J dot dA. And so what this is going to allow us to do is it's going to allow us to find what the current is in terms of the current density. And then we can evaluate for the current density from that. And so what we see here is the current is going to flow from the inside to the outside. And so what that means is there's some imaginary surface that is the outside of some cylinder that is going to be the area, so this could be some dA, that the current is going to be flowing through. And the reason why that's important is because we want to evaluate this integral right here, and so this is going to be J times A, where A is going to be equal to the area of this cylindrical shell. And so if this is some length of, I believe it says a length of W, so this is a length of W, this says that J times A is going to be J times 2 pi times R times W, or that J is going to be equal to I divided by 2 pi R W. Okay. So now we're ready to write what our two electric fields are. Like I said, we have two different electric fields because we have two different resistivities. And so the first one is going to be E vector 1 is going to be equal to rho 1 I divided by 2 pi R W. And the second one, and this is in the radial direction, The second one is going to be E vector 2 is going to be equal to rho 2 I divided by 2 pi RW. So we see here that the current density is going to be the same. And that should make sense because the current has to be the same. If you think about this, this is a system that's in series. And so when we have systems that are in series, the current is the same. And so the current density is also the same because the area that it's going to flow through is going to be this area that's changing as the radius. It's going to be the same area. Okay, so now what we can do is we can use these two to evaluate our integral. So delta V, what we're really doing is the negative integral from, this is some radius of A to some radius, I believe is F, because reasons. So this is from A to F of E dot dl. But what we realize is, and we already see this, is there are two different electric fields here. And so this integral needs to be broken up. So we have the integral from A to B of E1 dot dl minus the integral from B to F of E2 dot dl. Okay. So from here, there's just some algebra to do. But to make my life a little bit simpler, I'm going to factor out everything that's in common to this. And so I'm going to have a negative I divided by 2 pi W times rho 1 times the integral from A to B of dl is dr. So this is going to be dr divided by r plus rho 2 times the integral from B to F of dr over r. Okay. So when I evaluate these two integrals, what I'm going to end up seeing is that delta V is going to be equal to minus I divided by 2 pi W times rho 1 times the natural log of B divided by A plus rho 2 times the natural log of F divided by B. Okay? And then because we want to solve for the current, we just take this equation and solve for the current. We want this to be a positive value, and so I can take an absolute value and make this this positive. And then we can just solve this last equation for I. Okay? So as a process, it's a pretty straightforward question. We follow all the same steps that we always have when we have these resistivity questions. The thing that makes it a little bit challenging is the geometry. So this is going to be cylindrical, and the important thing to come out of this is that this area A is going to be this 2 pi r times W. Okay, so I'll pause here for a second and see if there are any questions, and then I'll move on to the next one. Okay, so on to the next one, and I'm recording this in addition to streaming it. So after I'm done with the live stream, I'll upload this video. So if you want to go back and pause it or go through it more slowly, if there's something that I go through kind of quickly, I didn't spend a lot of time on the calculus and the algebra. I just did it in my head and wrote it down. So if there was a step that didn't make sense to you here, you can go through it yourself to check it. Okay, so the next one is going to be problem 3 from 2007 or to 2017. So Emily has a question. If the current was flowing through the sides instead of the radial, the area would be the cross-sectional area. Yes, exactly. So if instead the current was flowing from left to right, then the area that this is going through, when I do I is equal to the integral of j dot dA, is just the cross-sectional area. And that's a very important distinction to make, that and this equation really tells you all that information when you think about it, because it's all about what the infinitesimal is that the current density is going through, and what the direction that points. So if it's going left to right, then that infinitesimal is going to be the cross-sectional area. Or if it's going outwards, it's the area of the outside of the cylinder. Okay, good. Okay, so for this next question, like I said, this is problem 3 from 2017. We have this setup here. So we have some cylindrical or spherical shells, I believe. So there's going to be some minus Q that's going to be evenly spread from some radius of A to a radius of 3A. So this is A and this is 3A. And what we want to do is we want to find the difference in electric potential between the center of the shell and the point 2A from the center. So what we want, and like I said, these are important calculations to be able to do. We want delta V between 0 and 2A. So this is 0 to 2A, okay? Where this is going to be E dot dl, okay? Let's see if I have a better piece of chalk. Okay. So in order to do this, again, we need to figure out what the electric field is. And so there are going to be two regions that are important here. We have the region where R is less than A, and the region where R is greater than A and less than 3A. We don't really care about what's going on outside or what's greater than 3A, because we're only finding the difference in electric potential between the origin 0 and the point 2A. And so that's somewhere that's inside the shell. So we could calculate the electric field outside, but we actually don't have to in this case. Okay, so we need the electric field. We know we have some spherical insulating shell. And so we can start by writing Gauss's law. So the integral of E dot ds is equal to Qn divided by epsilon naught. And then draw our Gaussian surfaces for these regions. So the first Gaussian surface is this one. And that's for R is less than A. And what we see here is that because this is some cylindrical shell of insulator, like this, when we draw this Gaussian surface for R is less than A, there's no charge that's inside here. So Qn is 0, which means that E is equal to 0. Okay? Now, the next case that we have is the region between A and 3A. And so that's the Gaussian surface that we have. It's a little hard to see because of the way that I shaded this, but that's the Gaussian surface there. Okay? And so here what we need to do is we need to evaluate Gauss's law. So integral E dot ds is equal to Qn divided by epsilon naught. The left-hand side is going to reduce to E times S. Because this is spherical, this is going to be E times 4 pi r squared. And this is going to be equal to Qn divided by epsilon naught. Because we have an insulator, Qn is going to be equal to the integral of rho dV. And now, looking at this, we see that we're going to need to know what rho is. So in order to find rho, by definition, the Rho the charge density is going to be equal to the total charge, total Q, divided by the total volume. And so what this means is I have this charge, is this minus Q? Or, yeah, it's just, this is a minus Q. This charge minus Q. So that's the total charge, divided by the total volume, which is going to be 4/3 pi times 3A quantity cubed minus A cubed, okay? And so we have what rho is now. Now we just need to set up the integral that we need to evaluate here. And this is a very important point. And if this is confusing to you, I would suggest playing this back a little bit later. So, and I'm actually gonna erase my shading here so that I can do some more shading here. So here's our Gaussian surface. Okay. And when we're finding Qn, it's the Q that's inside that surface. So this is what Qn is. We see that it starts at A and it goes up to the variable radius of R. It doesn't go all the way up to 3A because 3A is outside of the Gaussian surface. We only want the charge that goes up to the edge of the Gaussian surface. And so what that means is when I do Qn is equal to the integral of rho dV. dV is going to be 4 pi r squared dr because this is spherically symmetric. And this is going to go from A to R. Okay? And again, make sure that you understand why I have the limits of integration the way that I do. This is very important to understand that this charge that I'm adding up, it's really literally stacks of shells that I'm adding up. And those stacks of shells only go up to the radius of lowercase r when I'm inside the insulator. In this region, A is, or r is between A and 3A. Okay? So what that means is the charge density I have here is a constant. I can just bring it outside of the integral. And so when I do this integral, I'm going to end up having rho times 4/3 pi times r cubed minus a cubed. And we remember that rho is 4/3 pi, or it's minus q divided by 4/3 pi, 3a cubed minus a cubed. This right here, 3 cubed is going to be 27 minus 1, so this is going to be 26a cubed. And this is going to cancel here. And so what I end up seeing in the end is that this q in is going to be minus q times r cubed minus a cubed divided by 26a cubed. And so in the end, I can combine this. This is the q in. I can combine this with the left-hand side of Gauss's law. And so what I end up seeing is that, let me write it over here. E vector is going to be equal to 1 over 4 pi epsilon naught minus q r cubed minus a cubed divided by r squared a cubed times 36, not 36, 26. 26. Okay? And there's a unit vector here. So now we have our electric fields. We know in the region r is less than a, E is equal to 0. In the region r is between a and 3a. This is the electric field that we have. And so then what we can do is we can use those two electric fields to evaluate the difference in electric potential. So delta V is going to be equal to the negative integral from 0 to 2a of E dot dl, which is going to be equal to it's piecewise, right? But the portion where r is less than a, the electric field is 0. So really this is just the integral from a to 2a of this function here. So I'm going to take this function, I'm going to put it down here, and so this is just going to be, let's call this E2 and call this E1. This is E2 dot dr. Well, E2 now, E2 which is a function of r, times dr. Okay. And then what you can do is you can do this integral. Ultimately, you end up having this r cubed. When I divide by r squared is an r. This is going to be minus a cubed divided by r squared, and then just evaluate that integral. I'm not going to do that right now because I want to get through more problems, but that's ultimately what you do. So this problem, the big highlights are we know that we want a difference in electric potential. That means we need to find an electric field. Because this is an insulating shell, that means that we're going to apply Gauss's law. When we apply Gauss's law for the innermost region, we find that the electric field is 0. When we apply Gauss's law in the region between A and 3A, we see that we need to calculate what q in is. And when we do that, we see that q in is equal to rho dV, or the integral of rho dV. Rho is going to be the total charge divided by the total volume. So this is how I'm getting rho right here. Then I can evaluate this integral using rho and dV in spherical coordinates. Really important part right here, that the limits of integration are going to go from A to lowercase r, because that's where the charge is spread. I can do that integral. I find what q in is. That gives me what E2 is. And then I'm ready to evaluate what delta V is. Delta V is piecewise because I have two different electric fields. And E1, the integral over E1 is 0. The integral over E2 is just going to be the integral of this from A to 2A. Okay. So that's 2017 number 3. I'll let you guys ask any questions that you have while I'm looking for this. So 2010, number 1. Okay, yeah, okay. So yeah, I already answered Emily's question. Eric says for the problem 2017 number 4 and others like it, can we? I can't read. For 2017 number 4 problems and others like it, if we're given V, can we use R is equal to? Yeah. So Eric, I did it the way that I've been showing you, but alternatively, what you could have done with that problem, just to come back to this very briefly, what I could do is I could say that R is equal to the integral of rho dl over A, and then calculate what R is this way, and then say V is equal to IR. And so I, in this case, I is going to be equal to V divided by R once I calculate what the resistance is. Yeah, that's a perfectly fine way to do that. Yeah, this is you're more than welcome to approach the problem like that. I just did it the way that I've been doing it. Okay. So the next one is one that actually this one came off of the homework. This is problem 1 from 2010. It says an infinitely long conducting cylindrical shell has an inner radius of A and outer radius of B. There's an infinitely long line of charge at the axis of the shell with a constant charge per length lambda. Find the electric potential difference between a point inside the shell, a distance A over 2 from the center, and a point, a distance 2B from the center. Okay. All right, so this one says I have this line charge density lambda that is going to be at the center of this this shell here. And what I want to do is I want to find the difference in electric potential between the point A divided by 2 and the point 2B. So again, what are we trying to find? We're trying to find delta V is equal to the negative integral of A divided by 2 to 2B of E dot dl. Okay? And you guys should be seeing a pattern here. When we're asked to find this delta V, we need to find what the electric field is. And this is a problem that I'm dealing with conductors, and so that should lead us to want to use Gauss's law here. E dot ds is equal to Q in divided by epsilon naught. And so the regions that I have here, this is the radius A, this is the radius B. I have 3 different regions that I need here. The first region is when R is less than A. The second region is when R is greater than A and less than B. And the last region is when R is greater than B. Okay. And the reason why I need all 3 of these is because my limits of integration are going to go across all 3 of them. So I want to find the difference in electric potential between these 2 points. And so I'm going to need the electric field in all 3 regions. Now, we can do one of them very quickly because we know that this cylindrical shell is a conductor, which means that the electric field on the inside of it is going to be 0, which says that this electric field is 0. Okay? Now we need to worry about the region between for R is less than A. And so in order to do that, we can draw some Gaussian surface, give this Gaussian surface some length of L. And so when we evaluate Gauss's law here, the left-hand side is just going to be E times S. This S is going to be the surface area of the outside of the cylinder. This is going to be E times 2 pi R times L. The right-hand side is going to be Qn divided by epsilon naught. But Qn is just the total charge that's inside the cylinder, the Gaussian cylinder that I drew here. And if it has a length of L, and this is some line charge density of lambda, Q in is just going to be equal to lambda times L, right? Because dimensionally, lambda is charge per length. And I know that I want a length of L here. And so the charge that's inside here is just going to be the length of L times the charge per length. So this is divided by epsilon naught. We can rearrange this to solve for what E is. And so E vector is going to be equal to, my L's are going to cancel. This is going to be lambda divided by 2 pi r times epsilon naught in the radial direction. Okay? So that's my electric field for the region r is less than a. Now what we're going to need is the electric field in the region where r is greater than b. And so in order to do that, we draw some Gaussian surface like this. Now, in this problem, I don't know if it explicitly says this. It doesn't explicitly say there's no charge on this conductor, but we're meant to assume that there's no charge on the conductor. And so what that means is when I draw this Gaussian surface that encloses the conductor and the wire, there's not any additional charge that I'm enclosing from the conductor, which means that the charge inside is still going to be the lambda times L, if this is the same length of L. And so what it really says is that the electric field is the same in these two regions. So this is going to be E vector is going to be equal to lambda divided by 2 pi r epsilon naught times r hat. Okay. I'm running out of chalk that is of a reasonable size. All I have is these little chalk nubs, but we'll make do. So now that we have these two electric fields, or these three electric fields, we're ready to evaluate what delta V is. So delta V is going to be equal to the negative integral from A over 2 to 2b of E dot dl. This is going to be the integral from A over 2 to A E1 dot dl minus the integral from A to B of E2 dot dl minus the integral from B to 2b of E3. Let me move this over here. E3 dot dl. And this is r is greater than b. Okay. Now, when we're looking at these integrals, the first thing that we can notice is this one is going to be 0 because our electric field here is 0. So this is E1, E2, E3. And then all we need to do is plug in our electric field E1, electric field E2, and then evaluate these integrals. And so what we end up seeing here is that the first integral is going to be minus lambda divided by 2 pi epsilon naught integral from A divided by 2 to A of dr over r. And this is actually, this minus lambda divided by 2 pi epsilon naught is going to be common to both integrals. So we can factor out both of them. This is going to be the integral from b to 2b of dr over r. So this is going to give me minus lambda divided by 2 pi epsilon naught times the natural log of a divided by 2. This is really just the a's are going to cancel. This is the natural log of 1 over a half. 1 divided into half pieces gives me 2, plus the natural log of 2. Then I have 2 natural logs of 2, and so that's going to cancel the factor of 2 there, and then this is what I have. Again, I'm going through the algebra pretty quickly because that's not the important part. So if this is confusing to you, post on Slack and ask questions, or just make sure that when you go through this you understand how I got here. That on the exam, out of the points that this would be worth, this might be worth like 2 points out of 25. This isn't the important piece. Okay. And so something that a lot of people have asked when they look at the answer on this, they see a positive sign. And the positive sign instead of the negative sign has to do with what direction I integrated from. So we know that the integral of f of x dx from a to b is equal to the negative integral from b to a of the same function. And so depending on what direction you're integrating this, you get a positive or negative sign. Again, I'm not really that concerned about that. Now there is some interesting physics in that negative sign when you think about it. So to picture this, we can go back to talking about gravitation close to the Earth. And so this is to say I want to move a particle between the surface of the Earth and some point H here. And I want to know what the difference in the potential energy is. Whether I move it up or whether I move it down is going to either increase or decrease the potential energy. So if I calculate what the change in potential energy is to go up here, that's going to be positive. But if I find the change in potential energy to go down, that's going to be negative. And that's really what's going on here when you have this this negative sign. It's a matter of did I calculate this electric potential going out, or did I calculate the electric potential going in? You find that negative signs actually carry a lot of information like this when you look at problems. But for us and for our exam, whether you have a positive sign or a negative sign, I don't really care. You could have this as plus or minus. The important part is did you have this, and do all of the steps that you have, some of which I erased, do they lead up to that answer? Okay. So that was Amir's question. Karison wants to see 2015 number 3. So 2015 number 3. Okay. So this one is actually, in a way, fairly similar to the question that that we had. Actually, it's very similar to this exact question, but the difference is that now instead of having this this lambda charge density here, I'm putting some insulator in the middle. Let me just erase the whole thing. It's going to be too hard to draw it in what I drew already. So instead, with this one, you have some insulating solid piece in the middle, where this has some charge Q that's uniformly spread on it. This has some total length of L. And the radii that we have, because reasons, are this is a radius of A. Let's do this here. So this is a radius of A. This is a radius. This is a radius of B. And again, because reasons, this is a radius of F. And what we want to do is we want to find the difference in electric potential, and they draw this picture on the side here, which makes it easier to see what it is we're trying to do with finding the difference in electric potential. That made it look worse. Between the center and distance of D. Okay? So like I said, this one's actually pretty similar to the last one that we did. The two differences are that this is some insulator now, and that instead of giving you what the charge per length is, I give you what the charge is. Okay. Right. So we want to find delta V is equal to the negative integral of E dot dl between 0 and D. And so what that means is we need to find what the electric field in 4 regions. 1, 2, 3, 4. Okay. So in order to do that, we can say the regions that I'm interested in are R is less than A, R is greater than A, and less than B. R is greater than B, and less than F, and R is greater than F. Start off with the first one that's really easy to see is this one. The electric field is 0 because this is the region that's inside the conductor. Now to do the electric field in the region for R is less than A, this is to say that I need to evaluate Gauss's law. So this is the integral of E dot ds is equal to Qn divided by epsilon naught. This piece right here is going to be E times S, which for us, in this case, here's our Gaussian surface for the first part. And actually, I'm going to be lazy. I'm going to do something that's the entire length of this. There's an approximation that you have to make, and if some of my superiors or other people that are more familiar in the physics were watching this, they probably wouldn't be happy with me doing this because of the approximation, but I don't really care. This cylinder that I have here has some surface area. That's to say that this is going to be E 2 pi r times the total length of L. Okay. Now we need to evaluate the right-hand side of Gauss's law, and so that says Qn is equal to the integral of rho dv. To do this integral of rho dv, we need to find what rho is. Rho is going to be the total charge divided by the total volume. And so this is going to be equal to Q divided by the total volume of this cylinder is going to be pi a squared times the length, which is L. So this is going to be pi a squared times L. Okay. So now we're almost ready to evaluate what Qn is here. Qn is going to be equal to, this one is going to be equal to Q divided by pi a squared L times the integral from 0 to R. Again, very important point. When I draw this Gaussian surface, it has some radius of R. And I only want the charge that's inside this Gaussian surface. So that's why this upper limit is going to be R. And then dV is going to be 2 pi R times dr. 2 pi r L. 2 pi r L times dr. Okay? So what we see is our L's are going to cancel. We can cancel a pi. When we integrate, this is going to be r squared divided by 2. That's going to cancel the 2 that we have here. And so what we see is that Qn is going to be equal to Q r squared divided by a squared. So what that says, and I'm running out of room for this over here, is that the electric field in this region, R is less than A, is going to be E vector is going to be equal to 1 over 2 pi r times epsilon naught times Q times r squared divided by a squared times r hat. So this is E times S here. Okay. So that's my electric field in that region. The next region is going to be the region between A and B. And when I do that region, if I enclose the entire thing from this end to this end, again, you have to be careful because you're really making an approximation here. I'm just enclosing the total charge Q. And so that means the left-hand side of Gauss's law is the same. I still have this E 2 pi r L. The right-hand side is going to be hold on, something's funny. Something's funny here. This isn't an L here. This is no, it is an L here. It is an L here. Something happened. Something happened. Something happened. I need a factor of L here. I need a factor of L here. This L needs to be over here. Yeah, that's what happened. Okay. And you can see that that's the case because the dimensions of the denominator ultimately need to be r squared. So r times L gives me a meter squared. Yeah, so I was missing a factor of L here. Okay. So now when I do this in this region, I'm enclosing the total charge Q. And so that says then that the left-hand side is the same. The right-hand side just has a capital Q for Qn. And so this says that E vector is going to be equal to Q divided by 2 pi R L epsilon naught in the R hat direction. This one was 0. And now this one, when I'm enclosing the whole thing all the way on the outside, there's no charge on the conductor, which means when I go from this region to this region, I'm not actually enclosing any more charge, and so this electric field here is going to be the same. E vector is going to be equal to Q divided by 2 pi R L epsilon naught times R hat. Okay? So now I have my electric field in all of these regions. So call this one E1, call this one E2, call this E3, call this E4. Delta V is going to be equal to the negative integral from 0 to d of E vector dot dl. This is going to be equal to the integral from 0 to a of E1 dot dl minus the integral from a to b of E2 dot dl minus the integral from b to f, and these should actually all be lowercase. So this is a lowercase a, this is a b, this is a lowercase b, and then this is E3 dot dl, and then minus the integral from f to d of E4 dot dl. Okay, this one right This one right here is going to be 0 because the electric field is 0. And then all I need to do is I need to plug in my electric fields E1 here, E2 here, E4 here, and then evaluate the integrals. These two are going to give you some natural log. This one gives you an r squared after you integrate it, because this is going to be r squared divided by r, and then that's the integral of r dr, so I'm going to have a factor of r squared from this one. Okay, so like I said, I'm not going to go through that calculation. We did almost the same calculation for these two parts, and then this one ends up just being an integral of r dr in the end, times some constants. Okay, so Brooke asks number 4 from 2014, am I caught up here? So does potential energy decrease as you move further away? It depends. It depends on if you have a negative charge distribution or a positive charge distribution. But let's say that we had a positive charge distribution like this. If we had a positive charge distribution and I move and I have a positive charge that I bring close to here, there's more potential energy the closer that I am. So the further away that I am, the more the less potential energy there is. But that's actually the opposite if this is a negative charge. But funny things happen with some negative signs with the potential energy. And we didn't really talk about that, and it's not something you really have to worry about. But in terms of what do these electric potential functions look like, we can actually just plot it for a point charge, and I think that would illustrate pretty quickly what it is that I'm talking about here. So, say I have a point charge as a positive charge. The electric potential from this charge, the electric potential function is going to be 1 over 4 pi epsilon naught q divided by r. And so you can see if I plot this function, the closer that I am to the origin, the larger the electric potential. Which means that if I brought in some positive chest charge here, so this is like some plus q0, the closer I am here, the larger the potential energy. Which should kind of make sense on an intuitive level, because of the functional dependence of the electric potential on the radius, the closer I am, the larger the electric potential, the more force is trying to push this away, right? So, and you can think about that kind of like a spring. right? So the more you compress a spring, the more potential energy you have, and that in turn tells you the more force is working against you trying to compress it. The opposite is true if I have a negative charge. So if this is a negative charge, my electric potential looks like this. So like I said, funny things with negative signs are happening here. So when you get closer, the electric potential is smaller as a value, but as an absolute value, it's larger. And then you're tending towards 0 as you're going to infinity. Okay. That was about the negative sign. Yeah. That, ultimately, that's kind of a way to think about it. The negative sign, and it depends on what your electric field is. I don't want to say always this is true because it depends on what the electric field is. But if this is an electric field from a positive charge, it has this type of behavior. So the closer you are, the larger the electric potential. The further away, the smaller the electric potential. Okay. So where was I last? Brooke, and let me check and make sure I didn't miss any above this. Brooke's asking 2014 number 4. I already did 2015 number 3. So 2014 number 4. 2014 number 4. Ah, this is a good one. I like this one. And this one's just different. It's weird compared to some of the other ones, but it's a really good question. So I think it's kind of funny because there's some inverse relationship between what I think is a good question and what you guys think is a good question. I think a good question is a question that's dissimilar to the other ones. So you have this arrangement here where you have some spherical shells of resistivity. So this is a radius A, this is a radius of B, and then this is a radius of G. And we know that the region for between A and B has some resistivity that I believe is a constant. Yeah, so this one's a constant. And then this one on the outside is some function. So this is rho as a function of r, where rho as a function of r is going to be equal to rho 0 times r squared divided by g squared. Okay? And so what we say here is that we connect one end of a battery to the inner surface, and then we have this lead that's kind of floating around over here. And what we want to do is we want to find what the current is if I connect this lead at B and if I connect this lead at G. Okay? So in order to do this problem, ultimately what we need to do is we need to know what the resistance of these two shells are. So I'm actually going to do this the way that, that Eric had suggested. So previously I was doing this like starting with microscopic Ohm's law and deriving everything through. But for this one, I'm actually just going to say that dr is going to be equal to rho dl divided by A. And so what I want to do here is say that there is some resistance R1 here and some resistance R2 here. And the two cases that I'm connecting this with, if I connect it at this inner surface and then in the middle here, this is like saying I have this arrangement. So to draw it in a circuit diagram, it looks like this. The second arrangement, so this is R1 and this is V. The second arrangement is like saying I have the battery, I have R1, and then I also have R2. Right? So the key here is if I want to find the currents that go around here, call this a current I1 and call this a current I2, I need to determine what the resistances are. The resistance R1 and the resistance R2. Okay. So in order to do that, I'm going to use this equation right here, where A is going to be just the surface area of a sphere. So this is 4 pi r squared. So for R1, this has some resistivity of rho 0. So R1 is going to be equal to the integral of rho 0. dl is dr. A is going to be 4 pi r squared. And to evaluate the limits, we need to ask ourselves, where does the resistivity start and where does it end? So this resistivity starts at A and it goes to B. Okay? So when we do this, we end up seeing that this is going to be equal to rho 0 divided by 4 pi times 1 over r with a negative sign evaluated from A to B. This is going to give me rho 0 over 4 pi times 1 over A minus 1 over B. I flipped this and then I got rid of the negative sign. So this should be 1 over A minus 1 over B, which is really just going to be rho 0 divided by 4 pi AB times B minus A in the numerator. Okay, so this is what R1 is. R2 is going to be the same thing, only instead of rho 0, I'm going to have this rho as a function of r, which actually makes this calculation a little bit easier, you'll see. So R2 is going to be equal to the integral. This one goes from B to G, because R2 starts at B, it ends at G. So this is B, and this is G. I mean, it would be more fitting if this went to like D2 because I'm doing R2, but that's a terrible joke. So this is going to be rho 0 r squared divided by G squared divided by 4 pi r squared dr. My r squareds actually cancel. So I'm just integrating over this constant. So this is just going to be rho 0 divided by 4 pi times G minus B. Okay, and that's R2. So I have my R2, I have my R1. And now what I want to do is to find current I1, I can go around this loop here. This ends up saying that V is going to be equal to I1 R1. So I1 is going to be equal to V divided by R1. To find what it is, I could just plug this in. This one. This is R1. And then same thing here. Go around this loop. This loop says that V is going to be equal to I2 R1 plus R2, or I2 is equal to V divided by R1 plus R2. And I need desperately to find better chalk, because I have like all of these like tiny little chalk nubs here. Okay. So that's this one. You can just plug in what these are. Okay. Let's see. Can I do 2008 number 3? Yeah, that'll be the next one. And then Sean asks, is there ever a reason to create an integral of a path or a loop where there are 2 batteries in series or otherwise? And how can we deal with resistors that are in between the 2 batteries? Okay. Yeah. I don't know that there's a question on, I'm sure there are questions on old exams where this is something that happens. I can't think of any offhand. But yes, this is definitely a situation that can happen. Actually, now that I'm thinking about it, there are a couple of examples that this happened. And it's just a matter of keeping track of your signs. I'll come back to Joyce's question after this. But just to make something up. So call this some V1, call this some V2. This is R1, this is R2. This is actually, this type of diagram is actually the way that you jump your car if you have a dead battery, right? You connect positive to positive, you connect one of the negatives to ground. But the point is that you connect positives to positives. So if we want to find what the current is here, let's label a direction for the current, say this is I. And Sean actually asked what happens if I put a resistor in here. No problem, we can do that too. So we can put some R3 here. So we label the direction of the current. Now we have to draw a direction of the loop. I'm going to choose to do my loop like this. Integral E dot dl is equal to 0, which says that when I'm going around this loop, I see the negative terminal of V1. This is minus V1. R3 is in the same direction as, or the current that goes through R3 is in the same direction as the loop. This is plus I3 R3. Then I see the positive side of the battery. This is going to be plus V2. Current here is in the same direction as the loop. This is going to be plus I R2. And then this part is going to be plus I R1 is equal to 0. So we can factor out, why do I have an I3? Because this was R3. The current's all the same here. It's just the same continuous loop, so the current's the same. So what I can do is I can factor out my I from all of these terms and then move my V's to the other side. And so this says that V1 minus V2 divided by R1 plus R2 plus R3, barely holding on to that piece of chalk, is equal to I. Okay. So this is oh, we're frozen. And we were doing so well. We didn't have any technical problems up until now. I really don't know why that is. I probably have to update some drivers or something. Hopefully this comes back quickly and I don't have to restart OBS like last time. Okay. Save those changes and I'm back. Okay. Yeah. So based off of where I was, I didn't get much further. Yeah. Okay. Okay. But here's the point. Yeah, it's not at all a problem if I have two batteries that are in series with each other. I just follow the rules. So I started my loop over here. I'm going around the loop like this. I saw the negative side of this one. Then I get to the resistor that's in between the two batteries. That's this term. I get to the next one. I see the positive side. That's this. And then you just follow through the rest of it. But the interesting thing about this, because you ask if I have to worry if I put an R between the two batteries. And on a theoretical level, and I mean this in terms of like the theoretical physics and the math, not like just a conceptual level, but on a theoretical level, there's no difference between having this R3 here and then having it over here. Because this equation is exactly the same whether I have this term over here or whether I have it over here. Which means that I can rearrange, as long as I don't flip the orientation of any of these things, I can put any one of these things in whatever order I want. Okay, so the current through all the resistors is the same, even if there's a battery in between. Yes, yep. That's exactly what this is saying. The current's the same. The only time the current is not going to be the same is if I have a junction. So if I put something else over here, call this an R4. The current through R1 and R3 is the same, but I see when I get over here I have this junction, so this current I that I had before is going to split, so this is going to be some I1 and this is some I2. So then I can say I is equal to I1 plus I2. Okay. So that's the only time when the current's not going to be the same. So putting more batteries here, it would change what the current is compared to if I had fewer batteries, but it doesn't change the relative magnitude of the current through each individual resistor. All the resistors, if I didn't have this here anymore. Whether I could put as many batteries as I want here. And like I said, adding more batteries would change what the overall current is, but it doesn't change the fact that the current through each one of these resistors is the same. Yeah. Why is V2? What if V2 is inverted? If V2 is inverted, that just means that, and let me go back to the way that it was before. If I had V2 like this, that means that when I get to my equation here, this was a minus V1, this becomes a minus V2. Because the rule is, when I go around, I see a battery, do I see the negative terminal, or do I see the positive terminal? So here I see the negative terminal, which means I see negative. And I get here, this is negative. And the way it was before, this was like this. And so that's why I had minus and then plus when it was flipped. So that's what flipping the battery does. But those are good questions. Okay, so to come back to what Joyce had asked, 2008 number 3. I hope I can do that one. 2008 number 3. This is an interesting one. Okay, get into some resistivity problems. And this one, the key to this problem is what is the area that the current is flowing through. And I really wish somewhere I had a better piece of chalk. I can't go and knock on the neighbors' doors and ask them if they have a cup of chalk. They probably don't have any chalk. So this one says a rectangular block of material with resistivity rho has dimensions L by H by W. If a battery is connected across the block as shown, a certain current flows through the block. If the battery is instead connected the way that it is shown, 4 times the amount of current flows through the block. What can you conclude about L, H, and W? So this is the setup that we have. So this is one orientation of this. And then the other one, then let me label this. So this is L, this is H, and then this is W. And then if we flip this so that now this is like this, where this length is L, this is W, and this is H, and then this is from this side connected over here. This current that I have here, we can say this is some current I. This has 4 times the current. This has 4I. And so what we want to do is we want to evaluate what the relationship between L, H, and W are. Okay. So there really isn't a better piece of chalk. So what we can do here to start with is calculate what the resistance of this block is in this orientation. We'll call that some resistance R1. And calculate what it is in this orientation. We'll call that R2. Okay. So R1 is going to be equal to the integral of rho dr divided by A, where A in this case is H times W. So this is going to be equal to the integral of rho dr divided by H times W. And this goes from 0 to L. 0 to L. And so this is going to be equal to rho L divided by HW. We can do the same thing with R2. R2 is going to be equal to, this is equal to the integral of rho dr over A. And really I should have this as a dx. It's not really a dr. It's a dx. It's not a radial or a spherical infinitesimal. This one says that this is going to be equal to the integral from rho of rho dx over A, going from this is going from 0 to H, right? Because this is the length that it's going through, and the area that it's flowing through is going to be L times W. So this is L times W in the denominator. Okay. So what this says is this is going to be rho H divided by LW. Okay. So this is equal to R2. This is equal to R1. Okay. So what we can say is that we have 2 equations. V is equal to I1 R1, and V is equal to I2 R2. Right. We have different resistances and different currents, but the battery is the same. This is the same V in both cases. Okay. Which says then that I1 R1 is equal to I2 R2. Okay. Now we want to use the condition that I2 is going to be 4 times I1. And so that says that I1 R1 is going to be equal to 4 times I1 R2. We can cancel our I1s. And then, yeah, I was thinking about taking chalk from the office, and I should have. I can cancel my I1s and then plug in what R1 and R2 are. So R1 is going to be rho L divided by HW. And this is going to be equal to R2, which is rho H divided by LW times 4, just times 4. Okay. So we can cancel our rows. We can actually cancel a W. And so what this says is that L squared is going to be equal to 4H squared. And I can take a square root of this. And when I do that, I end up seeing that L is equal to 2 times H. Okay? So that's what we were looking for. Uh-oh, I froze again. How long was that going on? Let's see. It's really irritating, actually. Okay. All right, we're back. Yeah, sorry about that. I'm not always looking at chat because I'm focused on solving the problem. But I'll give you guys a second to look at this, and I'll talk you through what I did again. So basically, we have these two slabs of resistivity, and it's actually the same slab. It's just whether it's in this horizontal orientation or whether it's in this vertical orientation. And so what we wanted to do is we wanted to calculate what the resistance is in this orientation and this orientation. And then when we calculate those two resistances, we know that we have the same potential difference across them, the same V. And then the problem tells us that the current through the resistor when it's vertical like this is going to be 4 times the current in this one. And so once I have what my resistances are, and I can write these equations for what the potential across them is, I can equate them and then plug in the fact that this current is going to be 4 times this current, cancel my I's. So there's a factor of 4 here, and then I plugged in my R1 and my R2. And then rearrange this, and when I rearrange this, I end up finding that L is going to be 2 times H in order for this to be true. Okay. Okay, so that was the first part of this one. The second part of this one says, if the two blocks are connected together as shown, so I want to keep my R1 and R2 because this is going to be important. Keep my R1 and my R2. If the two blocks are connected as shown, so we had this case. So we connect the blocks like this. And what we want to do is we want to find what the electric field is in each one of these. So we want to find E1 and E2. Okay. So in order to do this, the first thing that we can do is we can find what the current is through each one of these. And the reason why I know we want to find the current is because we know to find the electric field, we know that this is equal to, E is equal to rho J, and J is equal to, J is going to be equal to I divided by A ultimately. And the current's going to be the same in both of these. So the area will be different, but the current is going to be the same. And so what I can do is I can find what the current is by saying that really this is just a system with resistors in series. I can do my loop, draw a current. This says that V is equal to I times R1 plus R2. And so I is going to be equal to V divided by R1 plus R2. No such luck with the chalk. I is equal to V divided by R1 plus R2. And so to find what each individual electric field is, E1 is going to be equal to rho J1, which is going to be I divided by A1. And E2 is going to be rho times I divided by A2. And so this one, make sure I'm not frozen, we're good. This is going to be equal to rho times I divided by A1 is going to be this cross-sectional area, which is HW. And then this one, rho times I divided by, this one has a cross-sectional area of L times W. This one's L times W, okay? And so these are my electric fields. I have a vector here, so I should have a vector on both sides. And I'm not gonna write in everything else, but we can see that if I wanted to write what the electric field was in terms of the things that I was given explicitly, I can plug R1 and R2 into this equation, and I can take this equation for I and plug it in here. So I have everything parameterized. I just didn't write the final answer. If this was a question on the test and you did this, this would be perfectly fine. As long as you put boxes around all of these things. So I know R is in terms of givens. Both R's are in terms of givens. So R1 is in terms of these givens. R2 is in terms of these givens. I is in terms of those that R1 and R2, as well as the V. And then the E is just in terms of the I. So these all connect together, but everything's been determined. Okay? So let's see. What charge would reside on the rectangular surface H by W where the blocks are joined? Oh man, this one really goes and gets it, huh? So now what we want to do is we want to find what the charge is that is on this surface. So in order to do that, we can draw some Gaussian surface like this. And it's a weird Gaussian surface that we haven't used before explicitly. Basicus would have, because he likes the Gaussian boxes. I use cylinders. But you can see that if the electric field goes this way, then I can write Gauss's law so that the integral of E dot ds is equal to Q in divided by epsilon naught. The reason why I do this is because I want the charge that's inside the box, and I have what the electric field is on the left and the right. And so what that says then is that this has some ds vector, some dA vector that points to the left. This has some dA vector that points to the right. The electric field points from left to right here. So when I do this dot product to evaluate the integral over the closed surface, this is going to be E1 times the area here, which is going to be, this area is going to be H times W with a negative sign. So again, the negative sign comes from evaluating the dot product here. And then this is going to be plus E2 times the same HW. And this is going to be equal to Q in divided by epsilon naught. And so from this I can solve for what Q in is. And like I said, it's nice if what you do is you write your final answer in terms of the things that are given in the statement of the problem. But this is 100% correct the way that it is, because everything that I've written here flows into the next portion, so everything's defined. Okay, and that's going to be it. Okay, so I'll post the video of this session now, so you guys can go back and watch it again. I wish you the best of luck studying. I think you guys are going to have fun on this test. You've been working really hard. The questions follow in the same spirit as all the questions that we've been working on, but without making you panic, they are different. somebody took the makeup exam today, and they said that they thought it was easy, which means that I managed to make different questions that might have been easier. So we'll see. But like I said, I'll post the video after this, and best of luck continue studying. Okay, I'll see you guys tomorrow.